Take a word like bank and suspend it in a void. On its own, it has no fixed definition. It could be the edge of a river or a place to store money. To determine its meaning, you have to look at the words surrounding it. Language is relational. The bank by the river provides one definition. The bank approved the loan provides another. The meaning lives in the connections the word shares with the sequence. Early language models read the way humans do, one word at a time, left to right. They updated a running hidden state as they went. But this created a bottleneck. By the end of a paragraph, context had faded. The signal was nearly gone. The transformer replaced this sequential summary with self-attention. Instead of reading in a line, every word looks directly at every other word, computing its meaning simultaneously. Machine comprehension shifted from a process of reading to a process of comparison, replacing the human-like sequence with an all-to-all mathematical web. But processing everything at once has a consequence. In a simultaneous web, the model has no inherent sense of order. To a pure attention mechanism, the dog bit the man and the man bit the dog are identical because they contain the same set of words. To provide a sense of time, engineers injected a fixed mathematical signal into the token embeddings. They used sinusoidal functions, overlapping sine and cosine waves, to label each position in the sequence with a unique pattern. These waves allow the model to distinguish absolute positions and, by calculating the difference between signals, measure the distance between any two words. It's an engineering decision that bakes the concept of order directly into the input. Positional encoding provides the sense of sequence that the attention mechanism lacks by design, ensuring the model knows not just what words are present, but where they sit. Once the order is set, the model can begin the work of retrieval. For every token, the system produces 3 vectors: a query, a key, and a value. Think of it as a search. The query is what a word is looking for, the key is what other words offer, and the value is the actual information retrieved. To find a match, the model takes a token's query and compares it against the key vectors of every other word. This dot product calculation creates a raw score, a mathematical measurement of how relevant one word is to understanding another. These scores pass through a softmax function, which turns them into a probability distribution. Irrelevant words are downweighted, while words that provide the necessary context are highlighted. The final output for the token is a weighted average of these values. Because this entire process is differentiable, the model can use backpropagation to learn from data. It isn't programmed with linguistic rules. Instead, it discovers through training which words to attend to and which to ignore. Through this retrieval process, a word builds its own meaning by blending together the most relevant information from the words around it. But language is layered. A word might relate to a verb for grammar, a pronoun for reference, and another noun for general topic. A single pass of attention can only track one type of relationship at a time. The solution is multi-head attention, running 8 parallel attention operations at once. One head might track the sentence structure, another follows the pronouns. They operate in parallel, each learning to attend to a different aspect of the input. These 8 outputs are combined and passed through a feed-forward network, then the whole process repeats. Models like GPT-2 stack these layers 24 times, passing the enriched data from one layer to the next. This stacking creates a hierarchy of understanding. Early layers pick up surface patterns like nearby words. Middle layers model grammatical structure. By the final layers, the representation of a word encodes its abstract meaning, the kind of information that survives even if you paraphrase the sentence. By the time a token reaches the end of the stack, it has been transformed from a single word into a representation of its specific role in the meaning of the entire sequence. The designers built this mechanism to translate text. They believed they were modeling the specific way human beings use words. But researchers soon found that the architecture didn't require words. If you took an image, shattered it into a sequence of image patches, and fed them into the same mechanism, it outperformed the specialized networks that had been engineered for vision. In 2021, DeepMind researchers applied this to biology. By treating amino acids as a sequence, AlphaFold 2 predicted how proteins fold with near-experimental accuracy, a challenge that had resisted 50 years of specialized scientific effort. This generalized because the core problem, understanding how individual parts relate to a whole is the same whether you are looking at words in a sentence, pixels in a photo, or amino acids in a protein. These disparate fields all share an underlying relational structure. Self-attention wasn't just a discovery for language, it was a discovery of how to model the pairwise relationships that define the structure of the world around us.